All right. So we are going to get started now. Um, all right. So the first question was, since today's topic is a little bit longer, would we still be able to do a lab by tonight? The answer is definitely yes, because tonight's lab is not about addition. It's about base conversion, about stuff that we talked about yesterday. Yes. So okay, so can you guys mute the mic, please? All right, Curtis, can you mute your mic, please? Thank you. All righty. So what we're going to do today is to talk about addition. So we'll first start with addition in base 10, and then we'll transition to to base 2, and then we'll convert arithmetic operations into logical operations. So that's kind of, what we are going to do today. Oh, no problem, no worries. There we go. Okay, so the module is binary number addition, and I'm hoping most of you have had a chance to read a portion of it. And it's kind of, it's a lot to dig through, but I'm going to present it in a way, hopefully, that it's not difficult to absorb. Okay. All right. So addition is something that we have learned a long time ago, and and the base that we learn addition in is in base 10. Okay. Unless you have a interesting elementary or middle school or high school that will teach you addition in some other bases, but most of us um, you know grow up with base 10 addition. So we'll first talk about base 10 addition, and then we'll talk about base 2 addition. So we can read all that stuff, the modules, but we can also just use the tablet, because I can now go through a few examples, so that the presentation is a little bit more interactive and hopefully less boring. There we go. So I'm just maximizing the screen, make it as big as possible. All right, so we'll start with an example that was in the text. So we're going to start with 7 plus 5, and these are all in base 10. Okay. So when we add 7 and 5, most of us will go like, oh, it's 12, which is not a wrong answer. Okay, but at the same time, understanding 7 plus 5 being 12 is not going to lend itself to multi-digit addition. So the way in this class, the way we look at 7 plus 5 is it is actually 2, but with a carry of 1. Okay, so now we're going to say, so we'll start to assign functions, to perform, to give us the single digit result, which is our 2, and also the carry, which is a 1. So what we want to do is to define a function r, which is the single digit result, and we want r of 7 and 5 to be 2, and we want a carry of 7, 5 to be 1 in this case, because the r is really just referring to the single digit result, and then the carry is referring to the carry of 1 over here. So are we doing okay so far in terms of what the R function is and what the C function is? One returns the single digit result of a single digit addition, and then the other one returns the carry, the value of the carry after the addition. So do we have any questions at this point? Because now would be a good time to ask questions to clarify what R and C are representing. Okay, so I'm giving you guys a little bit of time to absorb this and ask questions.
Hey, Professor.
Mm-hmm.
Yeah, I just wanted to know if C was the value of the carry or whether or not there is a carry.
Oh, okay, that's a very good question. So we'll go for another one that has a carry of 0. So this is 7, and even though most of us would say there's no carry, we can always say there's a carry of 0. Okay, so I think that should answer the question. So R3, 4 is 7, because that's the single digit result of adding 3 and 4. And then the carry of adding 3 and 4 is a 0. Does that answer the question? That was a very good question.
Yes, yeah. No, I guess my it's not binary though, is it?
Oh,
It
these are
it
not
can
binary. We're doing base 10 right now. So I
right.
usually
Okay.
start with something that we are familiar with, and then we'll transition to a structure, and then to something that is new to us, which is base 2. So right now we are still
Gotcha.
dealing with base 10. So we good?
Yep.
Okay.
Thanks.
So now, since we all have taken C and C++, we will go ahead and see if I can make an R function. Okay, so int x, int y, and we want to see okay, and this is base 10, okay, so this is for base 10 only. And I don't want to pass the base as a parameter, so it's just going to be quote unquote hard coded for the time being. So the return value is actually quite simple because all it does is to say, okay, we have x plus y, but then someone is going to say, but that's not going to be working because 7 plus 5 is 12 and we just need the 2 of the 12. That's okay because we can always use the mod operator and mod it with whatever base we are dealing with here. All right, so that's the R function. And let's just take a look at the C function, the carry function. So we have x, we got y. And remember, x and y are supposed to be single digits, in base 10. So now we're going to say return, and I'm going to use a ternary operator. You guys will find that, I really like to use ternary operators whenever possible. So we're going to say if x plus y is greater than or equal to 10, which is our base, then we return the value of 1. Otherwise, we return the value of 0. There we go. So now we have just defined the functions R and C for base 10. Do we have any questions right now? No questions. All right. So if there are no questions, then we'll try to tackle multi-digit addition, but do it in a way that you are not familiar with. Okay. So let's go ahead and deal with a multi-digit addition, and we'll start with 905 plus I don't know, 400 and let's say 27. Okay. All right. So you guys know how to do this already, but I'm going to do it in a way where we have some extra rows. Okay. Um, so I'm going to call this x. I'm going to call this y, and I'll call this row q, and then we'll call this row k, and then we'll call this row s. So q is really just an intermediate result. K is K for carry. Okay, I know carry starts with a C, but I'm going to use K here because I already used the letter C for the function. So just to avoid confusion, K is representing the carries. S is for sum. Okay, so now we're going to do the calculation. So we'll also, indicate that we have digit 0, digit 1, digit 2, and this is digit 3. So using this notation, x0 in this case is 5, x1 in this case is 0, x2 in this case is 9, and so on. So do we have any questions about the terms, of this part of the discussion? The 0, 1, 2, and 3, they are designating which digit we're dealing with. And then the x, y, q, k, s, those are designating which row we're dealing with. Okay, if there are no questions, I will start with some definitions. Okay, so the definition is q of I is really just the r, the result of adding xi and yi. That's how it's defined. Okay, that's really just how q is supposed to be done. Okay, so just using that particular definition, we'll go ahead and compute all the digits of the q row. So right here, it is the single digit result of 5 plus 7, which is 2. And then over here, it is 0 plus 2, which is a 2. And then over here, we have a 3. And someone is going to say, but Tech, you have not taken into consideration of the carries. Well, that's the whole idea. We want to separate the consideration of the carry from the consideration of the single digit result of adding 2 digits in base 10 in this case. So now we're going to look at the k function. Okay, so k is a little bit more complicated because ki plus 1, okay, which means the next column, is going to rely on two things. it's going to rely on the carry of adding xi, yi, but at the same time, it also relies on the carry of adding qi, ki. All right, and most of the time, okay, when we are working with concrete examples, k0 is usually assumed to be 0. Now, there are other cases, when later on, we will not make that assumption anymore. But right now, we'll make that assumption. So k0 is known to be just 0, or it's a given to us. So we don't have to compute k0. But k1, starting with k1, we have to do some calculations. So let's find out what is k1 in this case. So k1 is the carry of adding x0, y0, and the carry plus the carry of adding q0, k0. Okay. So can someone tell me what k1 is supposed to be?
One.
Exactly. Okay, that is 1 over here. What about k2? So k2, if I expand, k2 is going to be the carry of adding x1, y1 plus the carry of adding q1, k1. So what would k2 be?
0.
It would be 0, exactly, because 0 plus 2 has a carry of 0. 2 plus 1 also has a carry of 0. So we end up with a 0 over here. And what about k3? K3 is going to be C of x2, y2 plus C of q2, k2. So what would that be?
1.
It would be a 1. Very good. Okay, so those are all correct answers like that. And now we have to compute the sums, okay? So now we'll have another definition, which is S of I is really just the single digit addition result of adding. This time it is qi, ki. All right, so based on that particular definition, what should go here? What should go to S0? It'll be the single digit result of adding 2 and 0, and that would be, it'll be 2. Very good. Okay, I'm seeing that in the text channel. The next one is going to be a 3. This is going to be a 3, and I'm done. And somebody's going to say, but that doesn't make sense. 900 and something plus 400 and something cannot possibly be 300 and something. It can be, because I do have an overall carry of 1. This is the overall carry, and the overall carry is basically saying, oh, we have actually another 1000, but we cannot represent that 1000 as a part of the sum. So this is where things starts to get weird, is because the number of digits are fixed. So if x, y both only have 3 digits, then the sum also only have 3 digits. But we are allowed to keep track of an extra carry, and we can just say, well, we have a 332 is the answer, but we do have an overall carry of 1 in this particular addition. So is that okay? Does everybody follow this, the definition of the terms, and also mechanically how we figure out the values of those terms? Okay, I'm not. Oh, okay. Here we go. So Joaquin is typing something. Okay, how do we know K0? It's usually given. So K0, you can assume it is given to you. I'm just looking at the Discord screen. Okay, here's another question. In these operations, will there be more than 2 numbers added? No, the answer is no because we'll first, if you have three numbers to add, we'll add the first two, and then the sum of the first two will be added to the third one. So that's how we can add multiple numbers. Okay, and then Janelle is typing. I'm gonna wait for the question. If you guys feel comfortable, you can use your voice to ask questions too. Alright, so the next question is, would k ever be greater than 1? Okay, we can answer that question. In that case, can the carry number be treated as Boolean? Okay, so right now we are not concerned about Boolean. Okay, so right now everything is still arithmetic, and we are just dealing with numbers and values right now. Nothing is Boolean at this point. But I do want to answer the question of, can the carry ever be 2? In other words, can both of the contributor of the k bit be 1s? Okay, that's kind of the question, right? So let's look into that, okay, because we want to see if it is even possible. So we want to look into a case where we want xi, yi, the carry of xi, yi to be a 1, and we also want the carry of qi, ki to be a 1 as well. So we're asking whether is that possible, okay? Is it possible for this to be a 1 and also for this to be a 1? All right, so first question. In terms of x and y, how big can they be? Now, we remember we're dealing with base 10 over here. So xi, which is a digit of the number that we're adding, and yi, which is a digit of the other number that we're adding, they can only go up to 9, right? So in the largest case, okay, we can only deal with a C of 99, which definitely gives us a 1 over here. But that also means what is going to happen to Q, because we know what Q is representing, because instead of looking at this as Q, we're looking at the R of 9, 9 in this case. Okay, and then the KI over here. So what do you think is R of 9, 9? What is the single digit result of adding 9 to 9? It's only 8, right? So, and Ki, can only, okay, so this kind of goes into a chicken and egg problem, because, if I claim that Ki can only be 0 or 1, then someone's going to say, but Tech, you are proving exactly the same theorem. How can you make an assumption of that theorem that you're proving right now? It's called proof by induction, but this is the wrong class to talk about proof by induction. But we'll just kind of say that we will just make the assumption that up to the index I, the carry can only be 0 or 1, cannot be 2 yet. Okay, so ki can be a 0 or 1. The R of 99 is 8. So when you look at the carry of 8, 8, 1, it's still a 0. So it is not possible to have, this is a very informal proof of it is not possible to have a k bit being a k digit being a 2. Is that okay? Are you guys kind of understanding the argument? It's not a formal proof. When we get to the binary case, I can give you a very formal proof. But right now we'll just kind of go like, yeah, it cannot happen. All right, cool. Okay, cool. All right. So now we basically have all the bits, right? So we have x2, x1, x0, y2, y1, y0, and then we have the q bits. Now remember how the q bits are defined, and then we have the k bits. Okay, the k bits are also defined in a certain way, and there's one extra k bit. Okay, because we want to be able to store an overall carry. And then we have the sum bits, right? So we have all of the sum bits here. And then based on the definition that we have talked about already, I'm just going to repeat the definitions over here. Q of I is R of xi, yi. K of I plus 1, which is the next column over, is C of xi, yi plus C of qi, ki. And then S of I is R of qi, ki. So this picture works for base 10. Do we agree that this is working? It's just a very unintuitive way to look at addition, right? But it really kind of captures everything that we do with addition. It's just like, why do we need these extra rows? We could have done it without, the Q row. Okay, well, it'll be clear why we do that. Okay, so I get some confirmation. Okay, very good. So now we want to move on to binary addition, because now we have just talked about base 10 addition, which hopefully we are all familiar with, and I extracted the structure of addition. Okay, so we got two numbers that we are adding, and then we have this row here representing the partial sum, or the single digit sum, and then we have this row here, just for the carry bits, and then we have this row here being the sum digits. When I said bit, it's actually digit. Okay, so now the question is, how do we move on to deal with base 2? Okay, so let's move on to base 2. Come on, give me a new page. There we go. So now we want to deal with base 2. And when we deal with base 2, obviously we want to redefine the R and the C function. Okay, just a little bit. Okay, by the way. So we have int x, int y. And remember, x and y are single digits. This time in base 2, which means x can only be a 0 or 1, y can only be a 0 or 1. And we're going to say return x plus y. Last time it was mod 10 because we were dealing with base 10. What do you think should go here after the mod operator this time?
Mod 2.
2. Very good. Exactly. Oh, okay. So that function that we defined earlier, we just hard coded the base as base 10. So if we want to change the definition to work with base 2, all we have to do is to change the 10 to a 2. Okay. Now let's take a look at the other one. This is carry. So we got int x, int y again. And this time we have return x plus y is greater than or equal to the base. And what is the base again? 2. Okay. And if it is true, we return a 1. If it is false, we return a 0. There we go. Ah. Okay. Well, in the case of a base 10, if you want to enumerate all the possible cases, for x being 0, then we consider y being 0 all the way up to 9. And when x is 1, we consider y going from 0 to 9. That's going to be a pretty big table because you have 100 entries in that table. But for base 2, it's not quite so bad, right? So we want to make a truth table here. So we have x, we have y. X can be a 0, and x can be a 1. So this is our truth table because x and y are independent variables. So when one is 0, the other one can be 0 or 1. Okay, so that's why we have 4 entries here. And I'm just going to say this is r of xy, and this is going to be c of xy. And we'll go ahead and fill in this table. Okay, what about r of 0, 0? That should be a pretty easy one, right? Because you have 0 plus 0, which is 0. 0 mod 2 is still a 0. Okay, all right. What about when x is 0 and y is 1? Then you have 0 plus 1. 1 mod 2 is 1. I'm hoping that doesn't sound weird because I'm hoping that you guys have all learned about the mod operator from CISP310. Would that be a fair assumption? Okay, I'm going to take it as a yes. All right, so what about the next one? Well, it's symmetric. Okay, addition is kind of nice because it is symmetric. So 1 plus 0 is a 1. 1 mod 2 is still a 1. Put a 1 over here. So the only thing that is strange is the last row, which is 1 and 1. So x is 1, y is 1. 1 plus 1 is 2. Okay, 1 plus 1 is 2. 2 mod 2 is a 0. It actually makes sense because in base 2, there's not a single digit to represent the value of 2. So you need to have a carry. Just like 5 plus 5 in base 10, there's not a single digit in base 10 to represent the value of 10. So you have to have a carry and go like, okay, I can't handle this value, but I need the help of the next digit to help to help me represent the value. That's what a carry is. All right, so now we are moving on to the carry calculation. When x and y are both zeros, obviously 0 is not greater than or equal to 2, and as a result, it returns a value of 0. When 1 is a 1, the other one is a 0, then we have 1 as the sum, and 1 is not greater than or equal to 2, and we still want to return a 0. So we got 0, 0. And the only time when we have a carry in this case is when x is 1 and y is 1. Because then we have 1 plus 1, which is 2. 2 is greater than or equal to 2. And as a result, we return the then value of the ternary operator. So we end up with a 1 over here. So I want to see if there are any questions about this particular truth table, which basically just give you it just enumerates all the possible cases with the R and the C function when we are dealing with base 2. So I want to see if anyone has any questions at this point. All right, I'm not seeing any questions. All right, so if there are no questions about this, then we're going to isolate some of these columns, okay? And I'm going to repeat the column over here. So we'll deal with the easy one first. Okay. So when you look at this particular truth table, if I did not tell you, okay, I can't really hide it. if I did not tell you this is the carry of x and y, what do you think this truth table resembles or is exactly? Aha, okay, so Eric is correct, okay? It is actually the same thing as an and. Oh, okay, so x and y also would give us exactly the same value for every single row. This is cool because what this means is instead of using the arithmetic definition over here, okay, I did not intend to leave behind that mark. Okay, there we go. So instead of using the arithmetic definition, now we can define the C function so that we only make use of the Boolean operator. Okay, so we'll say return, and this is where you have to be really careful because the way C and C++ define what is true and what is false is not quite convenient for what we are doing here. So what we still need to do is to say x and y question mark 1 colon 0. And someone may look at this and go like, but that's really redundant. We shouldn't have to do that. Well, technically we do, okay? Because in C and C++, anything other than 0 is true. So that means if you were to just return x and y, it can return 5, it can return 10, it can return -1, it can return 613. Those are all true because they're all non-zeros. So to avoid having that potential issue, now yes, I understand that most compilers would evaluate x and y and give you only a 0 or 1, but it's not guaranteed. Okay, it is just not guaranteed. So it's always good to have a ternary operator, and then specifically return a 1 when it is true, and the 0 is not the problem. Okay, false being 0, that's not a problem. And Jonathan is correct as well. We could have used x NAND y NAND x NAND y. Yes, but that brings up a very good point. Okay, Jonathan brought up a very, very good point, being, oh, so that means we could use that NAND 2 circuit that we have been playing around for a long time. We could have used that, okay, to compute the carry of adding 2 bits. Ah, that is cool. Okay. So thank you, Jonathan, for bringing up, we can potentially re-express the whole thing using just NAND operations, and we know we only need 4 transistors to implement a NAND 2 gate. So that is kind of cool, because now instead of using addition and comparison, we can now do the whole thing just using logic gates that we know how to implement using transistors. Very good. But now we are going to look at the other one, which is not so easy, but it's still not too bad. Okay, it is the R function. So 0, 0, we have a 0 here, 0, 1, we have a 1 here, 1, 0, we have a 1 here, and then 1, 1, we have a 0 here. And most of you would go like, that does not ring a bell. Okay, does not resemble any operator, any logical operator that we have used in C and C++. And you would be correct. Okay, there's not a single logical operator that can do this. Then what are we going to do, right? What are we going to do? Well, instead of using one single operator, maybe we'll just consider having an expression to do it. Okay, so the way we work out the expression is to find one expression that is true only for the second row, and then we'll find an expression that is true only for the third row, and then we'll do an OR between those two sub-expressions, and then the OR expression itself is going to get the job done. Okay, so that's kind of the trick that we're going to do here. All right, so we'll have the first one being not x and y. Okay, so not x and y, this is going to give us a false because y is false to begin with. This one is going to give us a true, right? So this is the only time not x and y is going to be true, because x is false, not false is true, y is also true already, so true and true is true. The other two rows would also give us zeros or false, because in this case y is false, so the conjunction is going to be false. And then for the last row, x is true, but we have a negation of x over here, so not true is false. One side of the conjunction is false, so the whole thing is going to be false. And then we'll do something similar. Okay, this time we have x and not y, and it's going to be false over here because x is false. It's going to be false here because x is false. It's going to be true here because x is true and y is false, but since we negate y, so now we have true and true. And it's going to be false over here because y is true, not y is false. So when one side of the conjunction is false, then the whole thing is going to be false. Okay, so we can see how this expression is true only for the second row, and then this expression here is true, but only for the third row. But someone's going to say, but Tech, we need both rows to be true in order to implement our R function. Well, then we just have to OR these two rows. Okay, so now we look at not x and y, or x and not y. So now we have exactly what we want. So yes, so if Jonathan wants to re-express this entire thing only using only NAND operators, it's going to be a little bit long this time. Okay, so I'm not asking you guys to do that, but we can do it, right? Because we know how to use NAND to handle just negation. We know how to use NAND to implement usual AND. We know how to use NAND to implement logical OR. So yes, once again, this entire expression, even though it looks really kind of ugly, can be done using NAND gates. Okay, all right, so that's good, because now we know that both the C and the R function can be done using the gates that we have been playing with. Okay, the NAND2 gate, making that consists of two P transistors and two N transistors. We can use, we can just, it's going to be a mess because there's going to be a lot of those, transistors, but we can do it. Okay, the key is it can be done using transistors. That is rather cool. So the other thing I want to mention at this point is we're going to introduce a new way to express logical expressions, and it's going to look confusing for now, at first, but hopefully at some point it's going to look okay. We are getting used to it because this is how, this is what computer engineers and electrical engineers use when they need to write logical expressions. Because the C way of using logical expressions is really lengthy. Okay, just think about all the ampersand that you have to write. So I'm going to introduce the shorthand, which is also introduced in the notes. Okay, but I'm just going to put it over here too. And it's easy. Okay, it is represented as just x, y. Kind of like multiplication. Okay, but in this context, it is logical AND. Or is going to look like x plus y. Okay, and negation is the same. Okay, I'm going to keep exclamation point because that's easy to type. And then we have one more. Okay, that one extra one is, what about this thing over here? Okay, so we'll express that entire thing, which is not x and y, or x and not y. That is known as exclusive OR, and the symbol for exclusive OR is a plus with a circle around it. So now we're going to use these shorthands, okay, on this side. The priority is still maintained, which means, negation applies to whatever is right next to it. It has the highest priority. Conjunction has the next highest priority. And then we move on to disjunction and then to exclusive OR. So if I don't use extra parentheses, we always apply the negation first, and then we apply the conjunction, and then last we apply the disjunction. Do we have any questions at this point about just the notation? No questions? All right, we're going to move on then. All right, so at this point, okay, let's take a step back and find out what we have done so far. So we started off with base 10, okay, as an example, and then we defined the R, which is the single digit result of an addition, and the C function, which is the carry of a single digit addition in base 10. And then we worked out a few examples. We established the structure of a multi-digit addition in that case. And then we transitioned from base 10 to base 2. So the only thing we had to modify was how we defined the R function. Instead of modding with 10, it is now modding with 2. We also have to redefine or modify the C function. Instead of comparing to 10, it now has to compare to 2 because 2 is our base. So other than that, okay, nothing new, nothing too crazy. And then we look at the table, and then we found that, hey, the C function is the same thing as a conjunction, so we can just use a conjunction to implement the C function. That's the easy one. And then the R function is a little bit harder, but we still figure out, how to do it, using, just logical expressions. And then we talked about the shorthand. So, this way I don't have to, waste time typing or writing the ampersand ampersand, and it just looks like x times y. And then or looks like a plus. Negation is still an exclamation point. And then we also define exclusive or, which is basically the same thing as this kind of longer expression over here. So I want to see if there are any questions before we proceed. All right, I'm not seeing any questions, so I'm going to proceed. So we'll first ask that one question, okay? Because just because we redefine R and we redefine C, it doesn't mean that we are redefining K. So Ki plus 1 is still defined the same way as before. It is still C of xi, yi plus. Now this is a real plus here. It is not a or, okay? Not an or. C of qi, ki. So now the question is, well, we kind of argued, previously that this can be a regular OR, can be a logical OR, because these two C functions cannot both return 1 at the same time for base 10. And I gave you a very informal proof. For base 2, I can give you a formal proof. Okay? So let's find out what that formal proof may look like. Okay? So I'm going to swap to the next page. And we'll start with C of xi, yi being 1. Okay? So what does that imply? How can the carry of adding xi and yi be a 1 in base 2? Well, first of all, how many cases can give us a carry of 1 in base 2? Exactly. Okay, so all of those answers are correct. Okay, xi, yi both have to be 1s. Okay, so that implies xi is 1 and yi is 1. And by the way, this is the mathematical symbol for AND. Okay. Okay. So what does that imply in terms of Q of I? Q of I is the R, the single digit result of adding xi, yi. So in this case, what do you think is the R function going to return? Exactly, it is a 0. Huh. So if it is a 0, doesn't that imply C of qi, ki has to be a 0? And in this case, it doesn't even care about ki. Ki can be 1, but because qi is a 0, then it cannot have a carry of 1 coming from adding the qi and the ki digits. Does that make sense? All right.
Yeah, that makes sense.
Okay. Thank you. Thank you for the confirmation. So now we're going to work the other way. Okay. What about if I confirm, if I say this is giving us a carry of 1, then what can we imply? Well, that means qi is a 1 and ki is also a 1. Because the only time the C function is going to return a value of 1 is when both arguments are 1s. Okay. Ki of being 1, I really cannot infer anything, or nor does it matter. But qi being a 1 implies that xi is a 0 and yi is a 1, or this is the mathematical symbol for or. Xi is a 1 and yi is a 0. Okay, so I want to pause here and make sure that everybody get this part. Okay, because if Q of I is a 1, that means the R of xi, yi is a 1. But the two cases where the R function will return a value of 1 in base 2 is when xi and yi are different. So one can be a 0, but then the other one has to be a 1. So that boils down to only two possible cases over here. Does that make sense? All right. So what does that imply? That implies the C, the carry of xi, yi, has to be a 0. So if I start with saying, okay, what if the carry of qi, ki is a 1, then I have to conclude that C of xi, yi is a 0. If I, on the other hand, if I start with assuming C of xi, yi is a 1, then logically it can only conclude that the C of qi, ki has to be a 0. So that means they cannot both be 1s. Okay, they can both be 0s. That's perfectly okay, but they cannot both be 1s. So if they cannot both be 1s, that means instead of using the arithmetic addition, the plus, I can use a logical OR. Because when you look at x, y being independent variables, so this x, y, okay, maybe I shouldn't use x, y because that really causes confusion. I'm going to use some other letters. We'll use u and w, okay? So being two independent variables, 0, 0, 0, 1, 1, 0, and 1, 1, we look at the actual arithmetic addition. This is addition. And then we have u or w, which is logical OR. So you can see how, for 0, 0, they are the same. For 0, 1, they are also the same. For 1, 0, they are also the same. It's only for 1, 1 that they are different, because 1 plus 1 is a 2, but 1 or 1 is still just a 1. But because of this reasoning up here, we know that this row does not happen, because the carry of xi, yi and the carry of qi, ki cannot be 1 at the same time. So if the last row is not an issue, this cannot happen. If this cannot happen, that means instead of using an addition, which is a arithmetic operation, now I can use just a regular logical OR. It is now okay to use a logical OR. So now we have converted everything to binary or logical operation, because now we can say for base 2, okay, this is only useful for base 2. K of I plus 1 is now C of xi, yi, and we can now say just use a logical OR. There's no need to use a plus. So just use a logical OR, and the next side is qi, ki. Are we doing okay so far? We have just gotten rid of the very last arithmetic operator. So now everything is using Boolean operators or logical operators, which we also know can be done using just NAND 2 gates, just a whole lot of them. Are we good so far? Any questions? All right. So there.
Excuse me. I
Yeah, go
have
ahead.
a two big question, but if you don't mind, like, how do we get a Q and K again?
This is how we. Okay, actually, they are defined even earlier. That's how we define Q, K, and S.
Or no matter the base is 2 or 10.
Exactly.
Okay, got it. Thank you.
Exactly. Sure. All right. Any other questions?
Wait, so I had a question. Wait, can you hear me?
Yeah, go ahead.
So my question is, what exactly were we trying to prove? I thought we were trying. So are we just trying to prove that it should be written as an or rather than a plus? Like, was that what we were trying to prove at the beginning?
Well, at the beginning for base 10, I kind of, sort of proved that they cannot be 1s at the same time. But for base 2, I was able to use the logical derivation to basically prove that if C of xi, yi, if the C value of xi, yi is a 1, then C of qi, ki has to be a 0, and vice versa.
Oh, so we were just proving that it cannot be 2, right?
Exactly.
Okay, cool.
We are proving the return value of the C function cannot be both ones when we consider k of I plus 1. When we can consider this equation here, this term and this term cannot both be ones. And it has to do with how qi is defined.
Okay, that makes more sense. Thank you.
Absolutely. So, it looks like we have enough information now, to kind of make an adder circuit, right? Because we like, well, okay, maybe not you, but I like to play with Logisim and actually get to see the circuit work, right? So we'll go ahead and create a binary adder circuit and see how we can make it happen in Logisim. And by the way, I'll just make it very clear at this point before someone make the assumption, and any assumption, is that this is not your lab. So copying this circuit is not going to help in any way. Not today, not in the labs that we're going to do in the future. Okay, because every single year, every single semester, someone would copy this particular circuit and turn it in as the lab for a future topic. So I just want to make it very clear, nope, it is not going to be useful for that case. Alright, so what we'll do is, now we can build a circuit from the ground up. I suppose we can do that. So to build a circuit from the ground up, I need exclusive OR. Now you can probably find that there's actually exclusive OR here. XOR is exclusive OR. So I suppose we can use this one too. Okay, so we'll go ahead and just use that one. And the first thing I'm going to create is called a half adder. Okay, so we'll go ahead and add a circuit, and we'll call this a half adder. So a half adder is going to have 2 input pins. It has got X and has got Y. It will have 2 output pins. One is the C, and the other one is the R of the single digit addition. So let's go ahead and label these things so that this way it is clear to us, which one is which one. So we'll just define this one as the R of XY, and we'll go ahead and designate this one as the C of XY. So in this sense, X and Y are no more than just identifiers for the input of this particular circuit. It is not necessarily representing the numbers that we are adding. It is just designating the parameters. So in this case, okay, it's not going to be that difficult, right? Because if we are allowed to use the exclusive OR gate, it would be super easy, right? Because you just have to pull the exclusive OR gate, change it to the narrow. I personally do not like my logic gates to be too big, takes up too much room. So this is our exclusive OR gate, and that's going to connect to the R pin, and then we need a conjunction. Okay, so here's a conjunction, same thing. It's too big because we just need 2 inputs, and we'll change it to narrow. And this is also a good time to let you guys know that you should never leave an input pin unconnected. Let me say that one more time. You should never leave an input pin unconnected. It's okay to leave an output pin unconnected, but not input pins. And the reason is, if you leave an input pin unconnected, then it still has a voltage, it still has a electrical potential on it, except that electrical potential is induced by usually RF frequency stuff. So it becomes basically just very unpredictable. If someone is using a microwave oven close to the circuit, it might have a tendency to go to ones. In the absence of a microwave oven, it might have a tendency to go to 0. And we don't want circuits to rely on, whether a microwave oven is close to it or not. So that's why, do not leave input pins unconnected. Logisim doesn't really know nor care whether input pins, some of the input pins are not connected, but I'm just telling you that if I see input pins unconnected, I'm gonna take points off. All right, so now we got the circuit called a half adder. Super simple, right? So you can look at XY, as the actual XY row. Then we have this one is being Q and this one is K. But you can also look at X as Q. You can also look at Y as K. Then we have part of what KI plus 1 is going to be, and this is going to be the sum bit. Okay, so that's why it's called a half adder, because we're going to have two half adders to make a full adder. So a full adder is going to handle one column in a multi-digit addition. So now that we have this component, let's go ahead and turn it into, look at the package. And I am going to label all the pins. It's just usually a very good idea to label the pins, because if you don't label the pins, especially between the R and the C, sometimes you forget which one is which one, and then it's not going to work out very good. So I'm going to label the pins. You can always reposition things a little bit later. So that's why I typically just kind of put the text annotation somewhere in the circuit and then just move them into place when I need to make it look nicer. Okay, there we go. So here's our half adder. So now we make a full adder. So to add a new circuit, and a full adder is FA. Alright, so as the name implies, a full adder is going to need two half adders. Okay, so we have one, and we can always duplicate to get the other one. But now the question is, what are we going to, what is going to be the input into a full adder? To answer that question, let's go back to the tablet, and it's over here. And we're going to look at an example. Okay, so we're going to look at this picture over here, specifically over here. Okay, so we need one half adder to do this part. Okay, that's one half adder, sort of, because it contributes potentially to K1, and then we need the other half adder to do this part over here, but it also contributes to K1. So that means, we are going to have x1 from the actual numbers that we're adding. One bit of x and one bit of y will contribute as the input to the entire full adder, and it will need K0, an input carry, and then the output is going to be the sum and also the carry bit of the next column. Okay, so those two would be the outputs, and these three would be inputs. Okay, let me make it more clear which ones are the input and which one are the outputs. So I'm gonna undo a few steps so that way it becomes more clear. Okay, so the inputs are these two and also K0. Those are our inputs. This is our output, and that is also our output. Okay, so now we want to make the circuit to do the same thing. So now we go back to the circuit here. So this time we have XY being actually the two 1 bit each from the two numbers that we are adding. Okay, so this one, we'll label this one as X, and we'll label this one as Y. Okay, and then getting back to the tablet, we know that Q is the exclusive or the R of the half adder, of the first half adder. So now we connect X to pin X or port X of the first half adder, like this. We connect Y to the Y pin of the first half adder. And then this R is going to be the Q bit, okay? The Q bit of the addition. So we'll go ahead and label this first. Okay, this is just a label. Okay, by the way, this label really doesn't do a single thing. Okay, when it comes to affecting the function of the circuit. So this is really just a label, nothing else. All right, so now we look at the equation again. So Q, K, exclusive OR. The exclusive OR between Q and K become the sum. Okay, so that means we're going to take this one, bring it to one of the inputs of the other half adder, and then we also need K over here. I think the better way to label this is xi, this is yi, and this is ki. So ki is an actual input into this overall circuit, and this is Q, and so the R coming out is going to be the sum bit. So, and we'll label this as S of I. Okay. What about these two carries? Okay, oh wait, I need to hook this up to the port Y of the second half adder. Okay. So are we still doing okay in terms of translating one column of the multi-digit addition into a full adder? Are there any questions about the full adder at this point? All right, I'm not seeing any questions. So if anyone has any questions, go ahead and ask. So this output pin is Ki plus 1. It is the carry of the next column. If I go back to the tablet, it'll be equivalent to this guy over here. So now the question is, how do we compute K of I plus 1? We have the carry of xi, yi. We have the carry of qi, ki. So what can we do? What do we do to combine those two into K of I plus 1? Exactly, Eric. Okay, it is correct. Eric is correct. We just use an OR. Okay, nothing fancy, just a regular OR. So we go back to gates. We pull a OR gate, or you can use it. You can pull it from the toolbar as well. So do the same thing. Turn it into narrow. Change the number of input pins to just 2. And we'll put it. Oh, okay. We have to put it over here. Okay. And 1 comes from the second, because OR is symmetric, so it doesn't matter which one goes to which input pin. There we go. So now we have a full adder. Okay, we have xi, yi being the actual being digits from the two numbers that we are actually adding. We have ki, which is the carry bit of this column, which is probably computed by somebody else's full adder. And then we have S of I, which is the result that we really want. And then K of I plus 1, which goes to the next full adder if there's one. So this is a full adder, and now we want to convert it into a package. So the way we look at this, the differentiation between these two screens is this is the function definition. You can look at this as the function definition in C and C++, whereas this is the prototype of a function. It defines the interface to the function, but it doesn't show you how it is done. This one, on the other hand, shows you how everything is done. Alright, so now we're going to have to label these things just a little bit. Okay, so we got X, we got Y, we got K in, carry in, and then we have the sum, and then we have K out or carry out. So we just have to move these things around. Oh, okay, wrong tool. Gotta use the selection tool. So Y goes here, carry in goes here, and then the sum bit goes here. And then K out. There's not enough room, so I'm gonna have to put it outside of the packaging. There we go. So now we have a full adder. Alright, so now we have almost everything that we need. We go back to the main circuit. I'm just looking at the time, making sure that we are doing okay there. Alright, so now we have a, let's say we do a 3-bit by 3-bit adder. Okay, so we have 3-bit for this particular input pin, and that's X. And we duplicate it to get our Y. And then we have one extra input pin, which is K0. Okay, so K0 has its own input pin. There we go. And we are going to need 3 full adders. Okay, so we're gonna have 3 full adders. So we got 1, 2, and 3. There we go. And we also have a sum, which is an output pin. It has 3 bits. Okay, I said 3, but there we go. And then we have an overall carry, which is our carry out, or in this case also known as K3. There we go. Alright, so now it's time to do the wiring. Okay, we are still missing something because we are still missing the splitters. So we're gonna, take a row. Yeah, sure, we can do it a little bit earlier. Because I set up my Fitbit to give me an alarm, to take roll, but I can always do it now. Alright, so the row taking activity, as usual, is asking you for a word, and that is just carry. Let me show you the answer first. Right there. So the answer is just carry. C-A-R-R-Y. But I have to release it first. So you're not gonna you won't be able to see it until I release it. Alright. So it's June 9th. Oops. June 9th. And the current time is 39. I'll give you guys up to like 45 to do it. 6:45 p.m. June 9th, 6:45 p.m. Save and publish. There we go. So I just type in the text channel the word used for today's row taking. And I'm going to go back to here because I have a whole bunch of splitters to create in this circuit. So it's going to be a 3-bit splitter, split 3 ways, like so. And then the splitter becomes a merger in order to feed to the sum pin. So we'll change the facing like that. There we go. Alright, so the rest of this is really just hooking up the pins and the bits. So bit 0 of X goes to bit 0 X of the first full adder, and then Y is kind of the same thing, and then K0 goes to K in of the first full adder, like so. And then bit 1 of X goes to the next full adder, x of the next full adder, y1, y1 goes to pin y of the next full adder, and then x2 goes to x of the last full adder, and y2 goes to pin y of the last full adder. And here comes the fun part. Carry out of the first of bit 0 becomes k in of the next full adder. K out of bit 1 becomes k in of k2 of the last full adder, and then the last k out becomes the overall carry, which is x3, and then the sum bit of bit 0 becomes the sum bit of bit 0. There we go. And this one goes to the next one, like that. And this one goes to the most significant bit, like that. And now we have the whole circuit done. So let's test it first, okay? So we'll go ahead and give it a try. We'll try 2 plus 2, okay? So 2 is 0, 1, 0, 0, 1, 0, and the result is 1, 0, 0, which is a 4 with no overall carry. Yeah, that is correct. Okay, that's good. Let's see what we're going to get when we have 6 plus 2. Okay, 6 is 1, 1, 0 in base 2, and 0, 1, 0 is a 2. So the end result looks kind of odd because 6 plus 2 is 0. But wait, it does have an overall carry of 1. That overall carry of 1 is specifying a value of 8 because it is K3. So everything is still working. Very good. Let's see if K0 is going to come in. It's going to affect the result, because if I specify a 1 for this K0, then we should have 0, 0, 1 as the sum. Okay, give it a try. Yep, okay, very good. And let's go ahead and just specify 1 as a 7. So x is now 7. So 7 plus 0 with no input carry, or the input carry is a 0, is just 7. But if I change the input carry to a 1, then we end up with an 8, okay, which is basically 0, 0, 0 as the actual sum plus a carry, overall carry of 1, which is our K3. So the entire circuit is working indeed. So let me take a look at the time. It's 45. So someone is going to say, are we done with this module? I thought this module is supposed to be long and difficult. What is going on here? Well, we are done up to... this is the wrong module. Okay, where's the other one? This one here. Okay, so we are now up to right before section 6. Section 6, says, but wait, there's more. And if you watch any infomercial, that's usually a clue that there's a whole lot more stuff, okay? So that is why we're not quite done yet. But the other question is, why are we not done yet? Okay, because it seems like we got an adder that works. It does work. It has one problem. The problem is, until the first full adder is done and the carry output is stabilized, you cannot really trust the output of the second adder, full adder. Until the second full adder has stabilized its carry out, you cannot trust the output of the third full adder. So this method is called a ripple carry, or carry ripple adder. Let me just put the term over here so that you can see it. This is called a carry ripple adder. Oops, cannot type. Oh, okay. And the problem is, if you want to add 2 integers, each one has 64 bits, then you have to wait for the carry out that becomes the carry in of the next one. it's going to have to propagate 64 times, which the other way to put this is a 32-bit adder is going to be twice as fast as a 64-bit adder, because the length of time for the adder to settle down to have the correct result in the end is proportional to the number of bits. Okay, well, if this is the only way to get things done, and it cannot be, there's no way to avoid it, then so be it, right? Well, fortunately, there is a way to get around this problem. Okay, there is a way to make an adder so that the amount of time it takes to finish the calculation is independent to the number of bits that we are adding. So that is why we have section 6 in the module, because section 6 is the beginning of the discussion of what we call a carry look ahead mechanism. Okay, so a carry look ahead adder is one where you can be adding 64 bits or 32 bits or just 4 bits. It would take the same amount of time. Okay, and it's a very interesting technique to get this done. So so you need to read this section before the class tomorrow if you want to kind of get a head start, because this stuff here is a little bit thick, a little bit, it does take a little bit more time to understand the material. So I definitely want you guys to spend some time to read the rest of this entire module, because even though section 6 doesn't look like it's really long, it is very important. Okay, we do have a lab tonight. Okay, because I'm just looking at the time, it's time to release the lab for tonight. So the lab for tonight is for base conversion, which is something that we talked about yesterday. So no worries about the addition thing being too long, because we are going to be working on something that is from yesterday. All right, first thing first, the passcode is octopus. Remember the drunk octopus that wants to use base 7 because it needs to keep one tentacle on the beer. So that's our passcode, octopus. And it's also due at the end of the lab session today, which is June 9th, 8:20 p.m. There we go. And then save and publish. All right, so you got your lab, and you have your reading assignment, okay? Because I want you guys to finish reading that particular module for binary addition before class tomorrow. And let's see, I don't think we have anything else for the screen share. Any questions? Okay. No.
It's just
Yeah,
base
go ahead.
conversion lab, and then
Sorry?
it's just the base conversion lab tonight, and then we're done.
Yep, exactly. All right. All right, cool. So I'm going to turn off screen share and also the streaming, and then I'll go off and get something to eat, and then I'll be back by 7 o'clock or so. All right.